So the last two sections of chapter 16 have to deal with what happens when we have one or more sources. In this case, we're going to be specifically talking about two sources. Now, we can have multiple sources. There are a few more concepts that get in with acoustics and relative intensity and loudness of sound that obviously we're not covering. But if you ever do take an acoustics class, we can get way more in depth with these concepts, but we're going to just talk about what happens when two sources interfere with each other. Now, before watching this, you should watch the demonstration with two speakers, because that's going to really kind of outline what's going on when we have multiple sources. So check out the demo with me and Schaefer when we have two speakers and we're kind of walking around the room and getting some intensity of different sounds. So when I have two sources, let's start actually by making them the concept a little easier, and that is, let's put these two speakers directly in front of one another, and let's pretend that the sound can just go through them and there's no issues. Now, if we place these two speakers, here's speaker one, here's speaker two, if we place them exactly one wavelength apart. Now, again, this is an area of compression. This is an area of rarefaction. Now, if they are exactly one wavelength apart, assuming that they are putting out an identical sound, the waves are going to interfere and travel on top of each other. Now, according to the concept of superposition, every point that these two are interfering with each other, then the net pressure will be the sum of the two individual pressures. So here, for example, I have two crests meeting together, or rather, two areas of compression. So since that these two are directly a multiple of a wavelength apart, these two sound waves are in phase with one another. So waves that are in phase, if they're in phase like this is, I have two compressions that meet at the same time, and they will interfere constructively. We will get constructive interference. And that means then, as my two compressions come together, our pressure will actually add together and we will have a larger amplitude. And that means that the stuff will sound louder. So where we're at this point over here, we're standing here, we're going to hear the superposition of both waves, and that'll be translating to a louder sound. Now, the only time this can happen is if the difference between the two speakers is a multiple of a whole number of wavelengths. So this speaker one and speaker two, right here, they are exactly one wave apart. They could be one wave apart, they could be two waves apart, it doesn't matter. As long as they are a whole number of wavelengths apart, we will get constructive interference, and then our amplitude will be larger than if they were by themselves. So that translates to a louder sound. So now let's change things up a little bit. Now I have two speakers, speaker one and speaker two. And speaker one is putting out this gold or yellow wave, and speaker two is putting out a magenta. Yeah, that looks about magenta. And now these speakers, before they were a full wavelength apart, now they're a half a wavelength apart. So speaker one is putting out this gold, and right here we have an area of compression. Speaker two is putting out the magenta, and at the same point in time, we have an area of rarefaction. So I have an area of high pressure combining with an area of low pressure, and with the concept of superposition going over each other, my net pressure is always out of phase, so my net pressure is always just the normal pressure. So in here we have some destructive interference. So these two wavelengths, if they're out of phase with each other, their distance apart is a number of either a half wavelength or any whole number of wavelengths plus a half wavelength. What does that mean? It means they could be a half of a wavelength apart. They could be 1.5 wavelengths apart. They could be 2.5 wavelengths apart. In those instances, though, we are going to get some destructive interference. And we'll talk in a bit about some of the consequences of that, mainly around noise-canceling headphones. All right, so here's another quick check. I'm infamously having all the answers already out there. Oh, well, I'll fix that for next year. No, I won't. All right, so we have two speakers. They are 8 meters apart, and they have a wavelength of 4 meters. So these two speakers are setting out identical sound waves. Now, the interesting thing is, as you heard in the demo video, is that there are going to be different areas of both constructive and destructive interference. So to do that, to understand that, let's kind of figure that out. So if we're saying our wavelength is 4 meters, that means it's going to go one complete cycle in 4 meters. It's going to go a half a cycle in 2 meters. And every 1 meter, it's going to go through another kind of phase. So we're coming in here. Boom. Okay, not bad. Now continue. I didn't like that last one. Hold on. Let me try that again. Down, up. All right. So that's speaker 1. That's the sound that it's putting out. Now, speaker 2 is putting out an identical sound on this side. So we go up, down, and up. All right, not bad. The iPencil is not exactly the most fluid writing utensil. I'll take Pilot G2 any day. So the question is what's happening at these different points? So depending on where you stand, you will have different experiences. Now, wherever we have our crests meeting together, we'll have constructive interference. So where do the crests meet together? Well, here at A, they're meeting together. At C, they're meeting together. And at E, they're meeting together. So at these points, we'll have some constructive interference. Now, what's happening then at B and D? Well, at B, the yellow is at a crest, the red is at a trough. We'll have destructive interference, and oppositely but the same, at point D, the red is at a crest, the gold is at a trough. So again, we'll have destructive interference, and then that will actually cause, technically, the sound waves to cancel out. So here's a quick little summary. If I have two identical sources of waves, I'll have constructive interference if the path length is any distance of the wavelength or any multiple of that distance. I'll have destructive interference if it's any multiple of the distance plus a half. So those are the conditions for constructive and destructive interference. Now, getting a little bit more confusing is if I have two loudspeakers instead of in front of another, now they're side by side and emits an inverse sound of each other. So here I have the red and the gold. Then there will be destructive interference and the sound will completely cancel out. And that's how we get into the concept of noise canceling headphones. So with noise canceling headphones, I mentioned this in the demo, your noise canceling headphones aren't just headphones. They also have a microphone, and that microphone acts as a method of picking up the outside noise. So speaker 1, we can pretend is the outside noise. So that's the actual noise that you hear. Speaker 2 are your headphones. Now your headphones are producing a sound, right? The music, whatever it is you're listening to, this lecture. Now, if it's noise canceling, or more properly referred to as noise reduction, because it doesn't cancel out the noise, but it does help reduce it, it's going to measure that ambient sound. Well, it's not actually ambient sound, right? It's technically pressure. It's the sound waves from the outside in terms of pressure. So it takes that pressure and it produces an inverted version of it, which adds together with speaker 1 and then creates a neutral pressure superposition. So noise canceling headphones is an example of destructive interference from two sources. Very simple concept, very elegant concept, but just a consequence of how sound works. Very cool. Now, when we talk about actual sound, we've talked before, sound is a spherical wave. So a spherical wave radiates out from the source. So in practice, sound waves or light waves, they're emitted and they go out in all directions as spherical waves. So now this picture might be a little confusing. The one that I do in the demo, way better. But here I have speaker 1 and speaker 2. Now these two speakers are putting out identical waves. Now just like before, this is an area of a crest from speaker 1 and a trough from speaker 2. And what is that? That is destructive interference. Here's this red dot. I have speaker 1 and speaker 2 both having crests, and that'll be some constructive interference, and then that'll make it sound louder. So destructive interference will make it sound quieter, or if it's perfect, which doesn't actually work in 3 dimensions, it would completely cancel out. The red has constructive interference, and that is where it will feel or sound louder. So we can take a look at the distances away and whether or not they're a multiple of the wavelength or half a wavelength, but we're actually not going to get into that. It's just more conceptual is all we have to worry about. So generally with spherical waves compared to perfectly linear waves, we actually get exactly the same formulas, just thinking about it as a spherical wave instead of as a linear wave. So delta R would be the distance away from the speakers instead of the distance between the speakers in a straight line. So that's the formula. Again, we're not going to be really using the formulas. You use it on your homework that corresponds with this portion, and that is it. We'll never again talk about the actual formulas for constructive and destructive interference. Just got to know it at the conceptual level. So here's a quick check. This actually leads us into the next section. Pretend like you don't see the check mark. Two speakers emit sounds of nearly equal frequency. At a point between the two speakers, it varies from loud to soft. So we'll actually get into this in the next section. How quickly or how rapidly does it go from loud to soft? Well, this is 340 hertz. This is 341 hertz. It's going to be every second we're going to get a loud and a soft moment. So it'll go loud, soft, loud. And we'll talk about this. This is a consequence of something called beats, which we'll look at in the next segment. Bet you thought this video was over. But anyway, a couple demos. We already did this identical sound. You can also feel free to check out this FET simulation. It is a two-dimensional wave simulation, which puts out some speakers, and you can like move a guy around to get the relative intensity and kind of look at that. But I think that this demo that we already did is perfectly great. So with that, we have one section left to cover, and that is going to be the interference of not identical sounds. And we'll do that in the next segment.